Yeah, great. Okay. Yeah, thanks so much for this kind introduction. And of course, also thanks so much for this opportunity that BLISS gave us to present some of our very recent research here at this beautiful speaker series. And yeah, before we actually will get started with talking about foundation models, in particular LLMs, and what they do, what we can do with compression, and how they are related to image compression, I want to spend like 1 or 2 minutes on what we're doing at Merantix Momentum, because maybe not every one of you has heard of us before. So yeah, we are a Berlin-based company and now exists for like about 6 years, and we are part of a larger ecosystem. And it was already mentioned by Justus before. We are part of this Merantix ecosystem. We're based at the AI campus at Berlin, which also hosts different events, like now also your paper reading group, and it's also the place for many other startups. And yeah, what we particularly do as Merantix Momentum is we deliver cutting-edge AI solutions to clients in a project-based setup, right? So we are not a product-based company, but we do a lot of projects, okay? Right? And what we do in this project is consulting, right? So mainly about AI strategy, but we also have a great developer team. So we develop machine learning and AI solutions. And if the client wants that, we also operate. Okay. And if you go to our website, you will also find out, oh, there's one slogan that reads like, we bring research into production, which also sets the stage for the talk today, because we have a research team, which is quite large for a 60 people company. We are now 5 team members. And yeah, we are also doing publicly funded projects. So actually, the one that is also funding this research is the More with Less project. It's funded by the BMBF. Okay, yeah, so now I'm excited to show you some of our research. And yeah, it will be about LLMs. So let's talk about that. So I guess you all heard of LLMs before, right? About ChatGPT and all the related models. So I think it does not deserve a big introduction. So you can really just dive in and start with an important observation, which is probably also not very new to you, namely that these models get bigger and bigger, right? So nowadays we do not only talk about billion parameter size models, but even trillion parameter size, right? I think the newest Llama 4 series the biggest model has over 1 trillion parameters. Okay, so that's one important observation. Something that is really good, especially for the open science community, is that more and more open weights models are released. Right, so you can download them from Hugging Face. So in principle, they are available to us. And another good thing is that their performance catches up more and more with the closed source models like ChatGPT or Anthropic or whatever. Okay, so that's a good thing. But the question I want to raise here is, does that automatically mean that these models are really accessible to normal people that have to rely on consumer hardware, right? So here on the slide, you see like a illustration of this Llama series. I guess you've heard of this one before, the Llama models, right? So now if you go with like the latest consumer GPU, which is this RTX 5090, which has like 32 gigabytes video memory, turns out that the biggest model that you can fit in like 16-bit precision is just a 13B model, right? So by far not the largest model that is available. I mean, we are now even far beyond 70B, right? So, and this is just about the actual model, the weight. So it's not about batch inference. It's not about training. Okay. So what I want to say is that open weights does not automatically mean that these models are really accessible to everyone. Okay. And like, I just mentioned this, right? So the situation is becoming more and more extreme, right? We have now like 400B models or even bigger, right? And it turns out also like the size of these models outruns the progress we have in hardware, especially in single device hardware, which is like governed by Moore's law, right? So now we have to rely on multi-GPU hosting, multi-GPU inference, multi-GPU training, right? So the situation is becoming more and more extreme. Okay, so what does that mean? That basically means that although these models might be open weight, the control basically is still with the big players we all know, okay? So the main, like the overarching question we want to raise or motivates this talk is what measures can we take to get back control over like the models, our own data, how can we run them locally, how can we still get access to these models, right? And well, there are several ways to do that. And well, probably the most obvious one that probably like comes to your mind first is, well, what we could try to do is we could do some model compression, which will be also the main topic of this talk. So the basic idea is quite simple. We want to take a large model and somehow modify it, like its weights in a clever way so that it actually fits on a much smaller GPU. Okay? Well, like compression, of course, this is a very classical topic. It has been done before in many other fields in computer science, right? So we all know image and video compression, like JPEG or PNG. We know audio compression, like MP3. And just like to illustrate this a bit, right? So if you actually want to stream an Ultra HD video without any compression, you would need almost a gigabyte per second as bandwidth, which is insane. So it's not like available to normal people, right? So this like gives you a feeling that compression is really something that is important. And we see the same thing for large neural network models. Okay. Yeah, let's stick for a moment with image compression. I guess you've all compressed an image before, right? And typically what you have is this nice slider, right? So basically it allows you to set the target size of the compressed image. And at the same time, you get like a real-time preview of the image, and you can already inspect, is this size good enough for me or not? Right? So it's very intuitive and very direct. Okay. Something that is very desirable. Okay. Okay, now let's switch back to model compression. So here's like a teaser of one of the most popular methods that is like the gold standard now in compression, which is quantization, right? So what you typically do there, you take like a base model, which is mostly in 16 bits, right? And then there's a whole zoo of different quantization algorithms, which you can take, and well, you can reduce the bandwidth of the parameters of the matrices of these models. You can quantize them and end up with representations that are much smaller, like in 4-bit, 2-bit, or even less, right? So there are many different methods. And well, what you can already see here, there are discrete steps actually, and there are also other hyperparameters you have to take into account. So definitely there is no like just direct seamless slider which you can use here, right? And it's not so easy to say, well, when is it still acceptable? When are you cooked, right? So it's a quite complex parameter space that you have to explore when you actually want to use these algorithms in practice. Okay, so from that, basically, I want to formulate a little wish list from, like in our view, what a good compression algorithms for models should look like. So what we want is that model compression, is basically as easy to use as image compression. So we want to have direct access to this size performance trade-off, which you typically get with the sliders. We want to have full control over the slider. And of course, it should be fast, right? It should basically work in real time and should be seamless. We also want a flexible method that can be applied to any hardware that you are given and any like architecture. And it should also work well together with other compression algorithms, like complementary. And of course, most importantly, it should also give good compression results. So the actual, like the resulting performance should be still acceptable, right? Okay. So yeah, that's a wish list, right? So now let's switch gears a bit and become more technical, right? So, well, if we think of large language models, we'll know that most of them are actually based on this famous transformer architecture. And if you now zoom into this architecture, it turns out that most of the parameters, like in the attention blocks, like in the feed-forward blocks, most of the parameters, like 99% of the parameters actually account to linear layers, very, very large linear layers, okay? So a good candidate for compression is to say, okay, well, maybe you should consider compressing these large linear layers. And just like also to point this out, right? So typically you have like a hidden dimension, these transformer models. And for instance, if you double them, actually you will have like quadratic blow up, right? Because like you would double the input and output dimensions. So the size of the matrix is multiplied by 4. Okay. So that's another issue. Okay. Right. So that's like, I mean, there are other ways like how you can compress models, but this will be the main focus of this talk. Okay. Right. So as you can imagine, like compression is an old field. Also, like in the context of neural networks, it's like an old topic, right? It has been done now, like since deep learning appeared in the literature, right? And especially like also for LLMs, there's a lot of literature because like you have these huge models and there are hundreds or thousands of works. So it's impossible like to give you a comprehensive overview here. So if you like, you can go to surveys like this one and then start reading and get a good pointer, like a good starting point where you can dive deeper. So what I want to do here is to give you at least like a rough overview, a broad overview of like the main categories you have for quantization of big models. The first one you've seen before, right? In this example with the llama model. So that's weight quantization. So the goal here is that you take these large matrices and you want to reduce the bandwidth of these large matrices, right? So instead of like having these matrices like in full or half precision, like 16-bit, you want to somehow quantize these entries. Okay, and this is like, there are many ways to do that. And typically it's like a dictionary lookup, right? You want to like find good quantization weights. And you want to find good, efficient representations of these quantization dictionaries. So like in Infor, for instance, right? So if you want, you can also think of this as weight sharing, which I think is like the magic behind why this works so well in practice, because this really works surprisingly well. And this is why it's also, I think nowadays, like the most commonly used compression method, right? You can also download a pre-quantized models from Hugging Face if you like. But it does not come for free. Typically, quantization requires special hardware, right? So like to make this efficient in practice, in inference, right? So typically you maybe cannot use like the oldest GPU model. So there are some restrictions in that respect. And you've seen this before, there is no like this intuitive compression slider, right? So you really have to think about a specific algorithm, the specific quantization rate, and other hyperparameters that might be involved here, right? Okay, so that's one part. The next thing is weight pruning. It's still somewhat related. So it's still concerned with somehow modifying the entries of these large weight matrices. Okay. But here the goal is not to quantize them, but to actually prune them, to put them to zero, to basically sparsify these matrices. Well, it's quite obvious if you prune sufficiently many parameters, you can actually represent these matrices in a more efficient way. And again, there are many different algorithms. So this one here is the Wanda algorithm, which is also quite influential in the literature. So it's actually activation aware. So it takes like specific activations from calibration data into account. And this also works quite well. Like at least like if you do that, it turns out that the performance of these models is still good. And in principle, you now have like an option for a slider because you can basically specify how many parameters you want to prune, right? So it's a bit more continuous, right, than quantization. But it turns out that in practice, there are actually limitations. So for instance, you can think of like let's assume we have like a matrix that has 50% of its weights pruned, okay? I mean, it's sparse, but not super sparse, right? So it's not immediately clear how you would efficiently represent that matrix in memory, that you actually save some memory, right? So you really have to think about like how you actually do this. And there's also inference, right? So how do you actually have to materialize the full weight matrix or not? So there are many things you have to take into account. So in practice, typically you have to rely on some additional structure that makes this more efficient. There's, for instance, a concept like called NM sparsity, where you would consider certain blocks and you would consider a certain amount of zero entries. So if you do that, you can achieve more practicable algorithms, but typically the performance becomes worse. So yeah, what I want to say is like in practice, you typically don't have this slider, right? So there are some restrictions. And finally, there's low rank matrix factorization. And this is, I think, somewhat fundamentally different. So here the idea is to really rely on a different matrix representation. So maybe you've seen this before in the context of the LoRa algorithm, right? Which is about low rank adapters, but here it really concerns the actual weight matrix. So what we want to do is we want to factorize this matrix into two factors, which is one tall matrix and one short fat matrix, right? So it's a typical representation for low rank matrices. And we can already see from this picture, if this rank of the matrix is small enough, you will actually get a compression, right? Okay, so again, there's this option for a slider because you can basically choose the rank. So how strongly you reduce the rank. And it works on any hardware because it's basically still just vector matrix multiplication. But like if you look into the literature, typically these algorithms, like performance-wise, don't work as well as the other two approaches. So yet, I mean, we'll also actually dig into that direction, go into that direction, and hopefully I will convince you that actually you can design competitive algorithms with low-rank factorization. Okay, so that ends the introductory part of this talk, and also gives you some overview of what is already known in compression. Yeah, now I'm really happy to show you what we did in that field. So this talk, actually, it's the first time I'm giving this talk and presenting this work in public. So it's a quite recent paper from us at Merantix Momentum. It's called Choose Your Model Size, Any Compression by a Single Gradient Descent. And it's joint work with many great colleagues. So it was really great pleasure to collaborate on this exciting project. Okay, so let's dive in. So this paper is about a method which is called ACIP. So that stands for Any Compression by Iterative Pruning. Okay. Hopefully in a moment you will understand why it has that name. What you see on that slide here is basically like it's figure 2 from the paper. It's like this mandatory schematic overview of a method that you nowadays find like in any machine learning paper. And if you see this for the first time, which is very likely, we will probably overwhelm because there's a lot of things going on here, right? So my goal for the next minutes is to go with you step by step through this figure, and hopefully in the end, all this makes more sense to you, right? What ACIP is actually doing. Okay, yeah, so first things first, let's start at the left-hand side, which is the first step called model reparameterization. Okay, so we start with a base model, obviously, right? So it could be a llama model, but could be any other like transformer-based foundation model. And as I said, right, typically these models have a lot of large linear layers that we want to compress, okay? And what we do is, I just mentioned this, we want to go for low-rank factorization. So probably like the first thing that comes to your mind, if you think back to your like first course in linear algebra, is, oh wait, maybe I can do some singular value decomposition. Right, so it's well known, it has well-known mathematical properties, some optimality properties if we think of like optimal low-rank approximations with respect to a certain matrix norm. So probably it is a good candidate for a low-rank matrix factorization. But here in this first step, we don't do any compression. We just like basically compute the SVD of the weight matrix. So it doesn't really change the model, right? So it's still the same model. And well, like the SVD is basically, right, this factorization into U and V matrix, which are orthogonal and have these singular vectors. And then there's this diagonal matrix sigma, which contains the ordered singular values. Okay? Right? And well, what you want to do is you want to somehow obtain a low-rank matrix. So what we do is we introduce another matrix. It's basically just a binary mask, which has some learnable parameters P. Right? And this is what we actually want to, tune, right? So this is something, right, which is now, they're all initialized with 1, so nothing changed yet. But in principle, if we prune a lot of these mask parameters, we will obtain a low-rank factorization, right? So then many singular values are gone. So that's the main idea, okay? Quite simple. Okay, so yeah, I will come back to this, of course, in a moment. But there's one more detail I want to point out here. So you see this additional thing here. So if you're familiar with LoRa, this will look very familiar to you. It's again like a low-rank adapter, right? So basically, well, it's just like it's initialized with 0, so it doesn't change the base model at the beginning. But the idea is, okay, if we tune such a thing as well, which is very parameter efficient, what we hope for is to correct for errors that we make when we actually prune some of these mask parameters, right? So if we prune some singular values, of course, like there will be some performance drop because we discard some information of the original model. So what we hope for is that maybe with some adapter term, we can actually correct for these errors, at least partially, okay? So that's the main idea. Okay, so yeah, as I said, nothing has happened to the model yet. So it's just like a different way to represent the base model. So now let's talk about the actual algorithm, which is like the key step, which is iterative pruning. And we want to go for an end-to-end approach, which is based on backpropagation. And for backprop, what you need is some objective function, right? Some loss function. And the one that we use is quite simple. The first component is just a task loss. So it is the one that basically should drive the model into the right direction. So if we have large language models, this will be likely loss that does encoders like good next token prediction, the standard cross entropy loss. And typically you do this like, if it's a general purpose model, you do this on some calibration data set like C4 or some other sets. So they're good candidates and they're also freely available. Okay, so that's a task loss, right? It's a data fidelity term. And then at the same time, we want to compress the model, right? And like we have a way to do that because we introduce these masks, right? So we want to prune these masks. And if you're familiar with sparsity and pruning, probably the first thing that comes to your mind is, oh, maybe I should try out some L1 regularization term, which is also theoretically well known to encourage sparse solutions, at least when you choose this lambda parameter in the right way. So basically we add another penalty term, okay? And right, if you optimize for this, it's well known, at least like in the linear case, it's even like theoretically provable, you will obtain a sparse solution with respect to these parameters P, right? Which you penalize here. But it also empirically translates to more complicated situations like neural networks. So it's a quite simple objective. And well, if we actually solve that thing, or want to solve that with backprop, we right, like these parameters P, they don't just jump from 1 to 0, right? But we do gradient descent, right? So we do gradient updates with every step. So in practice, what turns out that the situation will more look like that. So at every step, like, so this is like the time, the number of gradient iterations, each of these parameters of this vector P will be shrinked step by step, right? So it will be shrinked, pushed towards 0 until it actually becomes 0. So the parameter is pruned, okay? And it also turns out that different parameters have different shrinkage speeds, basically, right? So not every parameter P is shrinked equally fast. But yeah, probably like the least important parameter and the least important singular value becomes pruned first. So it's shrinked the fastest, right? So it's the least important one for the actual task objective that we care about, right? And then there's a second one and so on and so on. So there is a certain pruning order over time, right? If we run this for a while, more and more parameters will be pruned. And what you can do is you can keep track of the order of the parameters. And like basically, if you really plot this in practice, I mean, this is obviously just an illustration, but it really looks like that in practice, right? You can do that and you'll see that it really looks like that. And in particular, this is like a really smooth thing, right? So this is like a monotonic decrease. Again, these are the nice properties of L1 regularization. Okay. So this is what happens when you actually optimize this, okay? So what do we do with that, right? So now we prune parameters, okay, we get some compression, but what's the point here? So I just mentioned, right? So basically the pruning order gives you some kind of importance ranking of these parameters P, right? Again, like the one that is pruned first probably is like the least important one for the task loss. And then there's the second one and so on and so on. Because we just touched like the singular values, which are just like, it's just a diagonal matrix. These are just a very few parameters compared to the actual model size. It's just about like 1 million parameters. So what we do is we actually keep track of the pruning order of these parameters. So you can do that. It's just like a few megabytes in memory, right? You can do that. And what you get out of this is like a global importance ranking across all linear layers. Right? So basically, like for each matrix, you have one vector P, and then you have this for all linear layers, which are just a few hundred, okay? Okay, and well, it's like also quite common in literature to call this a score map, because it like every, like the pruning order basically gives us a score. What parameter is more important compared to all the others, right? There's a clear ranking, okay? So this is what we keep. And well, typically, like if you run this algorithm, it's not super costly, right? It just takes like about like 30 minutes. You run this for a few thousand steps. So it's not a super costly process. And also like this LoRa adapter, I mean, this is parameter efficiency. It's just like a few million parameters. It's not comparable like to the sheer size of this like billion parameter size model. Okay. So this is what we keep. And now we can basically forget of all what was just on the left-hand side. We just keep the score map, this order, and the low rank adapters. Okay. So in principle, like, it doesn't really matter where we got this from. This is just an order, and we have these error correcting low rank adapters. And now we enter the third stage, which is the actual compression stage. We call it any compress for reasons we will hopefully see in a moment. So what can you do? Like, you have this comment, you have this global ordering. And now if you think about this for a moment, you can actually very easily design a very simple compression algorithm. So what you can do is, you still have this parameterized, SVT parameterized model, right? If you say, okay, maybe I want to have a model that has 30% of its original size, okay? What I can do is I can now take my SCORM and say, okay, well, I should maybe like prune the first parameter, the second one, and so on and so on. I continue this until I actually reach 30% of my original model size. I basically can use a for loop for that, okay? And I have a compression algorithm. Okay, so this is not super efficient, right? Because there's a monotonic relationship, you can actually do a binary search, which will like speed up this like enormously. And so basically what you get out of this like is a compression algorithm that is super simple and it works in almost real time, right? So basically like from the original parameterization to go like to 30% to 20% or to 90%, it doesn't really matter. You can do this under a second, right? Almost real time, right? Because you run this binary search, it's like just 1 million parameters. It's like almost instant. And it's fully reversible because we have the SCORM guide. We can jump between the different compression levels. Doesn't really matter, right? So you can basically have a slider, right? So we can now slide through the different sizes of the model and materialize every of these compressed models. Okay. And just like non-technical detail here, like if you think, oh, so what do we do with this low rank adapter? We just keep the one that we obtained from the training. So it's a bit counterintuitive because like we pruned a lot of parameters, but it turns out that it actually works quite well across all different compression scales, compression ratios. Okay, so we just keep it. Okay, that's really cool because now we have like a compression algorithm. We can already check a few boxes from this wish list. So it's a very simple, it's like a ridiculously simple compression algorithm. So we just take the SCORM map and do the compression according to this SCORM map. Okay, it's super fast. It works in almost real time and it's seamless. You have like this continuous scale, right? You have full control over the slider, so there's no additional hyperparameter involved here. And because we use low rank factorization, there's no restriction about the hardware and the model that we're using as long as we have large linear layers. Is not really specific to the transformer architecture. Okay, so that's nice, but of course, like, well, the actual key thing is, I mean, it's pointless if you just have a compression algorithm, but it should also work well in practice, right? So like if you actually do that, it should also give decent compression results performance-wise. So these are the main open questions for the moment. So I didn't show you any trade-off curve yet. I didn't compare this to any like existing method, and so far I didn't like show you like how this can be combined with things like quantization. So this is the mission for the last part of the talk, which is about results from the paper. Yeah, so let's speak about that. So what you see here is figure 1 from page 1. So hopefully it gives you an answer to this question about performance trade-offs. Size performance trade-offs. So what we did here basically is we applied this ACIP algorithm to a series of 7B models. So it's quite representative, right? So the Llama series, then the European Mistral model, and also the Chinese Guan model, right? So always like the most recent version. Well, and now you can run this ACIP algorithm. You have this any compression property, right? So you can jump to any compression level. And now at every like compression level, you can evaluate a model with a metric that you're interested in. So one metric that many people are interested in the literature is perplexity on a well-known general purpose data set, which is C4. So I think it was originally released by Google with the T5 model. So this metric is quite commonly reported in the literature. Okay, and then with that, like you will see these nice, smooth, consistent trade-off curves. Okay, so yeah, but maybe if you're not super familiar with perplexity, which of course is not a problem, you might not really care about these actual numbers, total numbers, right? But one thing that is quite striking here, like because lower is better, is that the more recent models, which in principle should be more capable, are actually performing worse than like the older like llama models. This is, I think, quite counterintuitive. There might be several reasons for that, but I think like the best explanation, at least to me, is that like actually these older models were specifically trained on data sets like C4, right? And so they adapt better to the style, the tone, and like the vibes of this data set. And that typically leads to better perplexity, because perplexity basically measures like how well is my next token predicted, right? So that's basically perplexity, right? So it's nothing about like a cognitive capabilities of these models. Yeah, and we'll see other metrics in a moment, and hopefully then, yeah, right, this spurious, I don't know. It's a bit counterintuitive, but actually it makes sense if you think about this for a moment. Okay, so here's one more experiment, and basically we have the same curves now, like with the actual size and number of parameters, not just like percentage. It's the same models, but we now complement this by models of different size, right? So now we have like the Gwen 3B model here, and also some 13B-ish models, right? So what you can see from that is, okay, yeah, so these trade-off curves are still valid. So you can still see these like basically compression laws here, right? So there's still this trade-off. Okay, one thing, however, which I think is important to note here, is that there is still a clear gap to pre-training. So what I mean by that is, if you look at this like black arrow here, so let's say we take this Gwen 7B model, right, which is this dashed line is a green one. If we compress it like to like 40% of its original size, it's like almost 3B. If we compared it to the actual, like the performance of the base model, the 3B base model, apparently there's a clear gap, right? So you cannot expect like miracles here in the sense that, oh, I run this 30-minute algorithm and it will just beat my pre-training of the 3B model, which took like millions of dollars.
I was wondering, so in this situation, you compress, but then you don't fine tune again, right? You just.
That's a great question. We don't fine tune. I mean, we run this LoRa adapter together, but we don't do any fine tuning. I will show you another experiment that also contains fine tuning. So you will see some benefits from that, but still, this gap will still remain. But that's a great point. I will come back to this in a moment. Yeah. Okay, so yeah, I will come also back to this fact and then this my conclusion, and give you like a broader picture, a bit more broader context about this whole thing of pre-training versus compression in the end. Okay. Right, so I mean, this is nice from a scientific perspective. Probably like reviewers would expect such figures in a paper, but a practitioner would say, okay, this guy he talked about image compression and some sliders and all that stuff. So where is the slider? So hopefully in that slide you will see like that you actually can use this algorithm like a slider. So what we did here is like we compressed this, let's say, llama model with ACIP. Now you can like jump between the different compression levels, as I said, in almost real time, and you can basically evaluate a model at what they were designed for, which is prompt completion, right? So here in this case, we ask it, what is the capital of Germany? Right? You can just complete this prompt and, oh yeah, the llama model knows it's Berlin. That's great. And now you can move down the slider and see if it's still working. You do that. I mean, this is just an animation, but it's really fast on a GPU, right? You just maybe have to wait for a second or so. And yeah, it's still also at 3B, it still knows it's Berlin. And also at 30%, Berlin is still in the answer, but I think grammar-wise, it doesn't make perfect sense anymore. And then at some point, you're cooked. Okay? So, I mean, yeah, but this is good, right? So we've been basically moving the slider around and around, and you see, okay, yeah, probably I should stick with 40%. This is, I shouldn't go below, right? And this is the same what you do with image compression, right? You move your slider and say, okay, yeah, this is not good enough anymore, right? So this is like a more practical view on all this. Okay? Right. So yeah, now let's move back to these more boring figures. Another figure from the paper, basically the scientific version of the previous slide, because what you might care more about in these models like than perplexity is, okay, how do these models perform on some like more real world tasks, question answering or some knowledge task, right? So what you typically do is you evaluate your models on some zero-shot tasks. So there are many great libraries. We used here the ELUSA LM harness library, which really allows you to plug and play evaluate these models. So basically what you get is some accuracy score, right? And yeah, I mean, like you will still observe these trade-off curves. This is expectable and very nice. And what you can also see is that here, like the comparison of the 7B models makes more sense, right? So now, like the more recent models perform actually much better compared to the perplexity graph. So this somehow also shows you that maybe perplexity also, although it's really commonly used in the literature, is maybe not the best measure of capabilities of these models. So you should always take into account more different metrics, right? So there's no single number that will give you like what you want. It really depends on what you care about. But yeah, again, like, I mean, these are numbers, right? So like the total numbers are probably not super interesting because you can always hack these metrics. So all the models were not instruction tuned. So if you really care about this, like good question answering performance, probably you should go for the instruction tuning models and apply ACIP to them. Okay. Right. So yeah. So basically this checks this box about the trade-off curve. So you see many trade-offs now. And the next thing would be, so is this somehow like competitive with existing approaches? And again, like there are many different like approaches existing also for low rank factorization. And what we compared ACIP to is actually like the most directly related method that exists. They're also quite recent. Particular popular ones are ASVD and SVD LLM. So they rely on a similar idea. They want to do some low rank matrix factorization with SVD. Okay. But they are quite different algorithm wise. So because they are training free. So they don't rely on backprop. So basically what they do is they take some batch of calibration data, they pipe it through the network, they compute the activations for every linear layer. And based on that, they have some clever feature engineered rule how they actually choose that singular values that they keep and the ones that they prune, right? Right, so there's some algorithm behind it, so it requires some additional SVD-based feature engineering. So in our objective view, there's nothing really special about the SVD, right? So it's just like a simple loss function. The good thing with these algorithms, it's much less memory hungry because you can run this sequentially, right? So you don't have to rely on backprop. But you also lose this any compression feature. But you have to do recomputations for every single compression level you care about. And most importantly, and this is what you can see from this table, hopefully, is that they perform much worse, right? Especially for higher compression levels, like especially ASVD, like sure cooked, right? I mean, think like a perplexity above like 20 or 30 is really like basically you wouldn't use these models, right? Well, there's something you can do about it. So this also relates to your question, right? What you can do is you can do fine tuning, right? You can maybe insert introduce a LoRa adapter and run for many thousand steps some fine tuning, and actually you will see much better results. So you can recover some of the original performance. But, well, I would argue, okay, if you do that, then you rely on backprop again. So there's no point to using a training free approach in the first place, right? So what we want to say here, I think, is that, well, if you have to rely on backprop anyways in the end, then probably you should go for it because it leads to much simpler and more flexible approaches. Okay? Right. So, and there's one more experiment I want to show you. That's really about fine-tuning. Or the second part is, so the first part I want to show you here is about the complementary nature of ACIP. So, well, so as you've seen, we only touch these mask parameters. So we don't touch these U and V matrices, which actually account to most of the parameters in the model. So they are frozen. So nothing speaks against quantizing them, right? So like still, these are most of the parameters, so we can still run the standard quantization algorithm. So this one here is like FP4 quantization with bits and bytes. And you can do that. And apparently, it's also quite cheap. This like works quite fast. Well, you can do quantization. Okay, there's like, you get a huge boost due to quantization in terms of memory that you consume, right? That's really cool. There's a slight drop in performance, right? If you really take this point by point, which is due to quantization. Okay. But what you can clearly see, you can combine these methods. Okay. And well, if you really look at the numbers, you might also argue, okay, well, like the gain of quantization is huge, right? I mean, it's like, right? So you really like do a shift essentially, right? Yeah.
First.
We did. It's a bit tricky, right? So if you actually like in the end like compress the models, if you like multiply these matrices back again, so you have to think about like when do I actually quantize? But we did a similar experiment. We basically transferred. So we ran ACIP on quantized matrices because it's more memory efficient, right? So it takes less memory in the backprop, and we just use the score maps and the LoRa adapters and transfer them back to a full precision or half precision model. It works also quite well. So you can do that if you like. Yeah. Yeah, but like the point is here, right? So, I mean, you might say, okay, if I just compare this directly, like ACIP, this blue curve, and the gain due to quantization, you might, yeah, okay, quantization is much better. And yeah, like just in terms of numbers, it is. And again, like I think this is mainly due to this weight sharing property, which you implicitly use when you do quantization, right? So we don't do this with ACIP. So I think you should rather think of these two approaches as like orthogonal, right? So they don't really interfere much with each other. You can use one of them, but you can also use both of them, right? So quantization really is concerned with a parameter level compression. And then there's things like ACIP or related algorithms, which are operating on a representation level, like they're operating on a singular value thing. And this is like the main benefit. You can leverage both advantages, right? So you couldn't do this if I would prune, for instance, only the weights of the matrix. So I couldn't do like weight pruning and quantization at the same time. But with like structured pruning, like lower rank matrix factorization, you can do that. So that's a very nice feature. Okay, so that's one thing. And then now really coming to your question, what you can of course also do is you can say, well, I mean, for instance, in ACIP, we have this LoRa adapter anyway. So, well, I can continue fine-tuning this LoRa adapter for a few thousand steps if I like, right? And can hope for further improvements. And indeed, you can improve the performance here. So basically get like a constant offset, can push the perplexity or other metrics towards the better. And well, but we should be aware that this comes for a price. I mean, it's not just like a few more thousand steps of backprop, but it really also requires us to commit to a certain compression level, right? Because I actually like fine-tune this LoRa adapter on a very specific compression level. I fixed this one, and then now I run like for 20,000 steps LoRa fine-tune, which is many hours. Okay. So it comes for a high price, but if you really want to commit to say, okay, yeah, I want to have like 50% compression, you can definitely do that if you like, right? You can recover some of the original performance. So that's nice, right? So it also works quite well like with fine tuning. But this is also true for other things like ASVD or SVD-LM, which you've seen before. Okay, so I'm running out of time, almost done. So yeah, let's conclude. Okay, so what have we seen? So yeah, on the last slides you've seen like many curves, many results, and like hopefully I convinced you that I mean with ACIP you can obtain decent results, practical results. So it also works in practice. But I think like the really like unique feature, this is like the main thing you should keep in mind from this method, is it comes with this any compression feature. So basically it means you can immediately like an almost real-time jump between different compression levels on these curves. Okay. And this is something as far as we are aware, is really like a unique feature to this algorithm. So you don't have to rerun these full compression algorithms to obtain these results. And it comes then, of course, with these nice things like a slider, which are more intuitive to use in practice. And then, yeah, there are another like more technical things that are very nice about it. It doesn't change the input-output interface of your transform model. So it's like a drop-in replacement. It works together with, you've just seen that, with quantization. And like if you go back to this figure, the schematic overview, it turns out it has really nothing really special about transformers or next token prediction here, right? So you can basically apply this to any loss or any type of transform model or any large model with a lot of linear layers, right? So in computer vision or wherever you like. Okay, so it's a general concept. Okay, so that's like the pro points, but of course we should also like think of limitations. I think you have seen a few before in the talk, and one thing I want to highlight here is really like this gap between like pre-training or model distillation and like post-training compression. So basically, like, I mean, you have seen this like this example in the graph before, but in general, like it turns out that still, if you have these very cheap post-training compression algorithms, you won't reach typically like what you would get from actual pre-training. So here in this graph, so basically what you would do is you would start with a very large base model, like let's say a DeepSeek, like 600 billion parameter model. And okay, maybe I can run ACIP or some other post-training compression algorithm, and I will end up with a curve like that, which will give me, maybe I can do that like in almost real time, like jumping between the different levels. And then I could also do pre-training, right? So basically generate a scaling law, right? Which is like here illustrated as this red curve. So I could train a smaller base model, right? A smaller model, like maybe 300B or 20B or whatever. But this is like at a totally different order of magnitude in costs, right? So it's like $1 million, right? So what we want to do, of course, is like somehow closing this gap, okay? So this is what we want to do, right? And it's, I think, like an open question. I mean, we've seen there are candidates like quantization, which come with different downsides. So there's maybe a chance to do that. But what we basically dream of is like maybe at some point we only have to pre-train a very large model, or maybe, I don't know, Google does that for us, right? So the largest model we can, and then somehow it comes with all the other sizes included, right? So I don't have to retrain my full, like my 7V model or whatever. So it basically comes with something, maybe not ACIP, but something of similar nature, where I get actually these compressions for almost free. Right, which now still I would have to rely on things like model distillation, which is a bit cheaper maybe than pre-training, but still super expensive. Right, so this is like the North Star, and I don't know if this is actually possible, but well, why not dreaming? Okay, so yeah, and to become a bit more concrete, so the things that we would try out next is basically like to scale this ACIP algorithm, right? So you have just seen results for like 13B or so, but it would be really nice to see what is actually happening for like more capable models like 70B plus, right? And also, I think there's tons of different generalizations and algorithmic improvements you can do here. Maybe we move away from this SVD factorization. There are also other types of low-rank factorizations, or maybe something completely different, right? So this whole idea of any compression is actually more general. Okay, cool. And the last thing I want to mention here is that we also want to make our research as accessible as possible. So the paper obviously is online, so it's an archive. But we also today published the code. It's on GitHub. So there's the link on the next slide. And maybe if you don't want to run this full ACIP algorithm, if you don't have a GPU, you can actually download all of these models that you've just seen from Hugging Face, right? So they come with the code, the core code included. So basically just a few lines of code is enough to download the model. You can, if you have a bit more time, you can also run this on a CPU. If you have enough CPU memory, will be a bit slower. Yeah, so you can get started very quickly. And if we have a bit more time, maybe at some point we'll also make these models available with Ollama so that you can run them locally. And with that, I'm done here. Yeah, here are a few more links, archive, GitHub. There will be also a project website very soon. So the link does not work yet, but will be hopefully available very soon. Yeah, I'm super happy to take your questions.
Thank you very much, Brandon. That was a great talk. These slides, these explanations. Thank you so much. I have a lot of questions, but I don't want to
Absolutely. We asked the same question, and if I'm not mistaken, there is a backup slide here, which I skipped due to for time reasons, but it hopefully gives you an answer. So this is basically what you would do if without any training, you would just take the singular values themselves as a score map, right? So like just the order. So this is what you would get, right? So this is perplexity. Like the red one is fine tuning, like still not very good, but like the blue one is what you should look at. It's like it doesn't work. It doesn't work at all. So maybe like one of the reasons, like you see on the right hand side, is like if you actually plot like what parameters were actually pruned by ACIP, you see it's a very heterogeneous thing, right? So there's no like, it's not very regular. So it's not even like that, like the smallest singular values were like the first ones that were pruned. So you can see some gaps here, right? So it's, yeah. So just going with the singular values, like with the trivial approach, does not work.
Hi, yes, thank you for the talk. And I would have one question about when was the slide where you showed the last step of the ACIP approach? Yes, so first question, this is, as far as I understood, only unstructured pruning. You don't have like a inherent structure for the matrices in the end after the pruning step is done.
I mean, like the structure basically is the singular value decomposition, right? So like you keep like only these singular values that were not pruned. So that's what I would say is like the structure, right? So but not sure like if I fully understood the question, like, but there's no like structure in these, for instance, singular value vectors, right? So there's no like a block structure or such thing, right? So it's fully unstructured when you just care about the actual mass parameters. Yeah.
And have you maybe also tested what the performance on latency was, or like the impact on latency, or like how fast the model runs?
I don't have a backup slide for that, but yes, we did that. And maybe there's for good reasons we didn't show that. I mean, yeah. So basically what you turns out that you won't observe any significant gains in latency or inference speed. And I mean, there are several reasons for that. So typically, I mean, it's somewhat difficult to actually measure inference speed or latency in a fair way because like it really relies on the hardware that you have, like how many parallel computations you can actually do. It really depends on like what batch size do you choose, right? So what I want to say is you can actually hack these matrices. So maybe that you would observe some gain, but if you just run this with like a normal setup with a small batch size, typically you don't observe any inference gains. And maybe the reason for that is that due to this low-rank vector factorization, you actually have to do 2 vector matrix multiplications, right? So instead of like one vector, like multiplying one vector with a very large full weight matrix, you have to do 2, right? With smaller matrices, but for like these particular implementations of the GPU kernels, it doesn't matter too much. So I'm not saying that you cannot achieve this, but for a standard setup, typically it's more about saving memory than gaining inference speed. But these are very preliminary results. And it's of course a great point to take into account because this is also what people care about. But it also does not get significantly worse, right? So it's not like that the speed is super slow, right? But you cannot expect great gains here.
Yeah, I have a question too about the fine tuning. So I didn't quite understand why you always try to evaluate without the fine tuning, because I think the idea of foundation models is to use fine tuning at the end of the day, right? And I think I've read a paper recently that argued that large language models should always be fine tuned before evaluation, especially because newer models, not in your case, but you usually have seen more data, so even some evaluation metrics that are used today. So that's the question about evaluation, and I have a follow-up on the method then.
Yeah, like about that. I mean, it's like if we really like would look into like our engineering projects, right? So we have one of our engineering engineers here, like if you would look into client projects, I wouldn't say for sure that fine-tuning is always the thing you would do in practice. So if you actually care more about the knowledge of the model, what you would rather do is some kind of RAG system. So I think fine-tuning is super relevant for instruction tuning and all that stuff, right? To basically make your model behave more or like generating outputs you want. But for instance, if you want to increase your knowledge, I'm not super sure if that fine-tuning is the way to go. It really depends on the use case. But yeah, it's right. So, I mean, basically, ACIP would be like just a starting point, right? So you would say, okay, I go for that. I inspect my model. And then maybe if I say, okay, this seems to work well enough, this compression level, then I should do some fine-tuning, right? So we also came up with some ways, actually, I mean, this is just like a teaser and this super preliminary. We also came up with some ways how you can actually preserve this any compressed property, even if you're doing fine tuning. So there's some things you can leverage about this any compressed property. So maybe there's also a chance to combine all this with fine tuning, which would then also resolve this issue if we would have to do fine tuning anyways. But it really depends on the situation that you're in practice.
Yeah, so that's my follow-up question would be, in the method you had those steps where you had a loss function, could you directly fine-tune there basically? So if you use the fine-tuning data for that loss.
Yeah, absolutely. Absolutely, yeah. So here, I mean, that's a great point. I mean, we didn't explore this too much, to be honest, right? So for like, if you have a very specific task you care about, let's say like some data set you're given, probably you should just reduce it right away, even for the ACIP algorithm. Why not, right? So you could expect that you will get some better gains actually, because typically this fine-tuning set is very specific. So you would expect that maybe the model does not have to know like what the capital of Germany is, but you only care about like very specific things, right? So you could even expect greater gains if you do that. Here, like for like academic purposes, we really focus on this calibration with C4, which is super common. But in practice, probably I would go for a very specific thing. But you could also do a two-step thing, right? You could first run this ACIP thing with a calibration data set, which is like still general purpose. And then you could go for some fine-tuning afterwards. So it's also possible. It's totally up to you.
So thanks for the talk. I have two technical questions, and I have to admit I'm not so familiar with the topic, so you sparked some interest. Thanks for this. So for instance, I thought you had this matrix decomposition, right? The high matrix times the like wide matrix, and you cannot really get better than training this setup with these two matrices. And when you just have like higher layer width, and like if you would train the model like with this setup instead of the full matrix, do you know, has there been some research with this? So for the same number of parameters, if you would just like choose a small layer width and like full matrices, would you have some benefits, or would it be worse than having this matrix decomposition? Do you understand my question?
So yeah, to just fully understand it. So basically what you say is like, I would just,
I know this slide before.
Basically tune U and V.
Yeah.
Compared to I would first prune them and then do it. So we didn't do that, to be honest. I don't know if like there's one work, it's called from Galor to Wheelor, which does something in that direction. Don't remember like all the details, but they do something in the direction that they actually fine tune U and V. Like the main technical problem here, practical challenge, is that fine tuning U and V is very costly because these are huge matrices, right? So yeah, in practice, it's not so easy to test out. They did some approach with some like lowering gradient updates. But I think like the results, at least to me, were not like super convincing, right? So there has to be more research done, definitely in that direction. And it's yeah, a perfectly valid question.
So I also thought if you could just like decrease the layer width, and the first thing that came into my mind was just using the dropout and just like taking a fixed like
Yeah, but for dropout, it's basically it's a random thing, right? So you don't know, like you would do like dropout during training all the time with different neurons. Right?
Yeah, but you could fix it and then just take one which performs the best, and then you have a smaller model.
As a matter of fact, there are related approaches. So basically, this would be like structured weight pruning. So if I go back to this weight pruning thing, right? So basically what you would do is you would like remove rows from this matrix. That's what you do, right? And people did this. And actually it's like somehow like suffers from the same problem as low rate matrix factorization because it's like a more restrictive approach. Typically you observe a stronger degradation of performance. So this is like neuron. There's also things like head pruning where people actually prune away certain attention heads, right? So you can do all kinds of pruning, and there has been done research on that. So yeah, absolutely, it can be done.
Thanks for the talk. First, I have to say your slides are really nice. They're very pretty. But second, so if you could go to slide 27, I think, or you show the fine-tuning. I just have a question about the graph. Yeah, here. So the curves, when you go on the very right side, they correspond to no compression, correct? Like the first node on the right, they all correspond to no compression. In that sense, so you can think of that as the algorithm not being, not acting at all. So maybe I'm just don't know enough, but why is the fine tuning better in that situation? Shouldn't the two nodes actually touch?
That's a great observation. It's a perfectly valid question. So yes, so there is some. I mean, I've shown you our like initial results, which you also find reported in the paper. And there was one reviewer pointing out a similar thing. And well, it's a bit mysterious, right? We don't do any compression, but apparently it's still worse than the base model. And actually, it turns out that it's not a bug, right? But there's a slight thing with our compression rule. So it's only related to this third step. So it's not about the thing you did before, right? You can still use the same score map. So basically, the reason for that is, and you can easily fix that, right? So I can show you like curves where you don't have this thing, right? We basically would perfectly match up the base model performance. The reason is that we actually keep the LoRa adapter across all layers. So there's one important detail I didn't mention explicitly here, but if you actually compress a matrix, yeah, like that. So if you do that thing, right? Just imagine like how many parameters would you get compared to the original weight matrix? Actually, it's more than that, right? Because you have U and V. So basically, if it's a quadratic matrix, you're doubling the weights initially. And that's not cool, right? So there are other similar approaches. It's the same like with weight pruning, where you have like 50% compression. You want to do this efficiently, right? So you actually double the number of weights. So that means that to actually get some decent compression, you have to prune a lot of singular values, right? More than 50% actually. After 50%, you will get some gains. And for most of the layers you do, but not for all of them, right? You don't do that for all of them. So there are some very important things, layers, like one in the very end. I've shown this slide before here. There are layers that are not pruned at all. No, this one is actually pruned. There are some pruners layers that, actually these layers, there are some specific layers, like the last one, this is not pruned at all. So what you do there, you basically recover the original matrix. This is what you do, right? So to avoid this doubling issue. And the problem is that we use the LoRa adapter still for these original weight matrices. And this was basically the reason why you observed this drop even for the base model. If you omit the LoRa adapters, which you can certainly do, you will get a perfectly valid curve. Was a quite technical answer to your question, but yeah, you can easily fix that.
No, thank you. I would have another question, but maybe I should pass it.
It has to be a good question now. Damn. So just basically pruning off the singular values that you don't need. It seems like a brutal approach, and you're kind of discarding information. is there a way to include this information, for example, by recombining rows or columns in your U and V matrix? So integrating basically the information you cut away, maybe by just taking the mean of the row and column, lowest singular value row and columns.
Yeah, I thought about this as well. So we didn't do any experiments in that direction, but yes, like in principle, it feels like a super brutal approach. I mean, people, as you've seen, like people tried this before, right? So you can do that and it works surprisingly well, but definitely there are probably ways to improve that, right? So like our approach is again like super like it's standard for deep learning, but we say, okay, maybe we don't know the best rule to do that. Maybe there is a good rule, but we don't know. So what you typically do in deep learning is, oh yeah, you introduce some generic weights, which in our case is this LoRa adapter, right? So which you've seen, right? So it's this LoRa adapter here, right? So this is what you say, okay, maybe we should correct for this, and we don't know how we should do that. And well, we just introduce some weights and we do backprop. So this is what you typically do if you don't have a good idea how you should design a model-based rule. Not saying that this is possible, or if you can maybe do both. Yeah, it's an interesting open research question if you could do that.
Okay, so I was supposed to give back the microphone now, but I also have a question. And that is, is it okay? Okay, thank you. So I think like, I really like your method, but I see like one thing that I would like to be explained, and that is, you said you argued with accessibility, right? Like you cannot run these models so easily locally, and your methods mostly picked models which are very much hostable locally, right? And I think it makes perfect sense because you need to run backprops. So probably if you run backprops on a 30B model, you already need like a H100 node or something, right? But as you know, scale this to like the 405B models, I bet you have like huge problems, right? So I'm wondering if you even achieved the goal of making it more accessible, since it has kind of this limitation that you need to run backprops once. And
yeah, I totally see your point. I mean, like doing the scale up is like, okay, maybe go to the conclusion slide here. That's like the next step we want to do, and you definitely will run into problems. So this is why I think like the main, like to make this more practical, right? Of course, like if you go beyond 13B, you cannot use a single GPU. Like we use H100s, which are like almost SOTA, right? And like you can fit a 13B model. Maybe you can do quantization, and maybe you will fit like a 30B model, but like at some point you're cooked, right? So you have to do some model parallelism or all kind of stuff. So the main idea would you say, okay, maybe you would need these resources to actually run this ACIP algorithm, but using that one here, right? This is the thing, right? We upload the model, right? So it's done. Like the backprop is done. We don't care anymore. This is still feasible, right? This is still feasible. This is like what I think is like the strength, right? You don't rely on this iterative pruning. Yeah, maybe you need a lot of hardware for that, and maybe like you cannot do this on your consumer GPU. But what you could still do is you could like run this code, right? So basically, we separated the full compression from the actual algorithm, right? So that would be my argument. Okay, yeah, well, 600B, that's challenging anyways, right? I mean, even like to download this model is challenging, but I mean, yeah. So that would be my argument. To say, yeah, okay, it's more practical than like if you would have to rely on backprop only, right? Okay.